Welcome to the second video of applications of moment generating functions. In the first video discussing applications, we looked at in particular three sort of useful uses of moment generating functions. We looked at the fact that a moment generating function can be used to specify the distribution. We also said that it could be used to compute the moments. And finally, we said that it could be used to analyze sums of random variables. In this video, we are going to look at point number 2, how it is used to compute the moments of a random variable. In other words, the expected value of x to the power of n. So, without further ado, let's begin. Here is my claim when finding a moment. For a random variable x, or an RVx, with MGF, or moment generating function, mx of t, the nth moment of x is, or can be computed by, expected value of x to the n is equal to the nth derivative of the moment generating function evaluated at 0. This is the notation, but in case it's a little bit unclear to you, this is what we're defining as the nth derivative of mx of t evaluated at t is equal to 0. That will be our moment generating function. So, how do I go about proving this to you so that you're satisfied? Because I want you to be satisfied that why does this work? Why can we just take the nth derivative, set it to 0, and we're done? And it's this important, very important feature. Let's take a look. So I'm going to start with the definition, or I'm going to start with the nth derivative first, and try and work our way and make our way to show you conclusively that it is xe to the expected value of x to the n. So again, remember the nth derivative is the derivative with respect to t n times evaluated at t is equal to 0. I'm now going to put in the definition of a random variable. I'm going to put in the definition of the expected value. And here it is here, dn dt. Remember, the moment generating function is given by e, the expected value of e to the tx. And we're differentiating this, and then we're going to evaluate at 0. So far, so good. Now, in the next step, what I want to convince you effectively is I'm going to try and convince you that I can take a derivative, I can take an expectation, and then I can differentiate it. Or I can actually first differentiate with respect to t and then take the expectation. Here's what I mean. Let me give you a bit more conclusive, something on a page that might solidify this. So think about the definition of expectation for a second. We have two definitions of expectation. One for discrete, where x is an element of the support, e to the tx times px of x. That's one definition. Now, what we have to do with this definition, technically, is we're going to differentiate with respect to t, and then we're going to evaluate at t is equal to 0. So far, so good. No issues. The other way that this could be formulated, or the way that this could happen, is that we in fact use the continuous version rather than the discrete version, and we say d and dt of, we use the continuous version of expectation. Its x is in the support of x of e to the tx multiplied by the probability density function integrated with respect to x. And of course, we differentiate with respect to t, and t is equal to 0 in this case. What's important here to see is that one of the important properties of differentiation, and let's look at the first case, for example. And in case it's not clear, this is, of course, the discrete case. This is the continuous case. So going back up to this first example, one of the properties of differentiation is we know that when we take a sum of functions and then we differentiate a sum, what we can actually do is we can instead, it is the equivalent of taking the sum of the respective derivatives, e to the tx times px of x. And I'll repeat that again. The derivative of a sum is the sum of derivatives. That is one of the key properties of differentiation. And again, we're still evaluating at t is equal to 0. Second one's a bit of a, not challenging, but rather a different approach. Again, recall that, integration is really just summation at the limits, right? We're not doing anything different to summation. We're just summing over very small discrete intervals as those intervals effectively tend to 0. So by the same sort of reasoning here, when you take a derivative of an integral, or derivative of an integral, we can actually say that is the equivalent of taking the integral of the derivative dt e to the tx dot fx of x dx. And again, by the same reasoning as before. Here's where it gets interesting. Let's look at both these cases. In both these cases, what do we get? Well, in the first case, we're differentiating something with respect to t. Now, px of x is independent of our variable that we're differentiating by. So in all respects, it's actually a constant. So our own focus, or our only focus, is really the e to the tx component. So what happens when you differentiate e to the tx once? So I'm just going to do an aside calculation. d on dt e to the tx. What happens when you differentiate once? Well, when you differentiate once, what you get is you get an x, or you differentiate with respect to t. So in this particular instant, x is the coefficient of t in the power. So you have to take the power down the front. So that gives you x e to the tx. Okay, that's not too bad. What if you were to take the second derivative? of e to the tx? Well, that's the equivalent of taking the derivative again of the derivative. And when you take the derivative of the derivative, again, by the same reasoning, you have a coefficient of t in the power, you need to bring it down the front, which makes sense. So we've got x squared e to the tx. And if I continued in this fashion, it would mean that d to the n on dt to the n e to the tx is actually going to give you x to the power of n e to the tx. So, by the same token, what we have here, going back up, is two different, we'll simplify our two functions here that we have. That is the sum of x is an element of omega of x to the n e to the tx times px of x. Again, px of x was a constant, so you just keep it in the multiplication, and we're still evaluating at t is equal to 0. The second component is x is an element of omega x. And again, same sort of reasoning here. Fx of x, the probability density function, is independent of the variable we're differentiating by. So in this particular case, it's a constant with respect to t. We're only interested in differentiating the e to the tx. We know what that is. It's x to the n e to the tx dot fx of x dx. And again, we're evaluating at t is equal to 0. So far, so good. Hey, what do you know? We've actually come up with a new we've come up with a new function, and they're very similar. Look at this. This first function is the definition of expectation of x to the n e to the tx in the discrete case. And this second expression here is the definition of x to the n e to the tx for the continuous case. So in both cases, it is by definition the expected value of x to the n e to the tx. Still, of course, we've got evaluated at t equals 0. Still got to do that. And finally, we can substitute directly a value of t is equal to 0 in this expression. It gives us the expected value of x to the n e to the t times 0, which in this case, e to the t times 0 is just e to the power of 0, or 1. And so we're left with the expected value of x to the n. And there you have it. After a long discussion, here is the proof that truly the expected value of x to the n can be evaluated using the nth derivative of the moment generating function evaluated at 0. So now that we've computed this, let's go for a specific example. In the following example, we're going to demonstrate how the moment generating function can be used to evaluate the expectation and the variance. Here is our question. Let x be a random variable with PMF and MGF given by the following. Now you might recognize this example from the first video where we had a probability distribution, PMF, where x is equal to a half and x takes the values -1 or 1, And we actually found in that example that the moment generating function had expression cosh of t. And t, of course, was an element of the real number line. So we could evaluate expectation and variance using the typical method of the definitions. But for now, let us instead try and use the moment generating function. So to do that, we're going to have to find derivatives. So here goes nothing. Let's start with the first derivative. So m prime of t. Let's find that first. That is the derivative of the moment generating function by definition. That is, of course, the derivative of cosh of t. Now, for those who don't know their cosh derivatives off by heart, we can actually use the definition of cosh first to evaluate it. And the definition of cosh is e to the power of t plus e to the minus t over 2. When we differentiate this with respect to t, we get this first term e to the t on 2. Differentiate e to the t, you just get e to the t. So that's just e to the t over 2 still. But then the second term, you've got a minus in the power. So you need to bring the coefficient of t, which is basically -1, down the front. And then that gives you minus e to the -t. And for those of you who are familiar, this is actually the definition of shine. Moving forward, we're actually also going to evaluate the second moment of the distribution function. The second derivative of the moment generating function, because the second derivative will help us evaluate the second moment. So in this particular example, this would be, we can actually say that is the derivative of the first derivative. So it's the derivative of the derivative, which in this case is d on dt of shine t, which in this case is d on dt. Again, if you're not familiar with the definition, that is e to the t minus e to the -t over 2. In this particular instance, this becomes, okay, the first term, the e to the t on 2, becomes just e to the t on 2 when differentiated. And of course, the e to the -t on 2 on the other side, well, the negative power has to come out the front, and it actually cancels with the first negative, leaving us with positive e to the -t. And behold, this is the definition, cosh of t. So, we've evaluated the first and second derivative. This now allows us to calculate the first and second moment. So without further ado, the first moment, expected value of x, is equal to mx prime of 0, which in this case, where was mx prime? Mx prime was the following function here, shine. So it just becomes shine of 0, which in this case becomes, using the definition of shine, which is this one above, becomes e to the 0 minus e to the -0 over 2, which in this particular instance, e to the 0 is 1, e to the -0 is 1. So you got 1 minus 1 in the numerator, 0. this evaluates to 0. In the opposite case, we've got the expected value of x squared, which is the second derivative evaluated at 0. We said before that the second derivative was just cosh. So we've got cosh of 0. In this case, cosh of 0 is equal to e to the 0 plus e to the negative 0 on 2 by definition. And in this case, we have 1 in the power plus 1. So it's the numerator is 2 divided by 2. We get a value of 1. And allowing that now, we can actually use the definition of variance, which we know to be the expected value of x squared minus the expected value of x all squared, which in this case is 1 minus 0 squared from the two above, which is 1. And of course, we could have computed this independently using the old definitions. You can do that in your own time. Convince yourself that it is the same. But I hope this video was helpful. In short, we've shown that the nth moment of a distribution can be computed using the nth derivative of the moment generating function at 0, and we've gone through an example. Thank you for watching. I hope to see you in the next video.